Greetings, mathematicians. Welcome to this little presentation on analytical geometry. Now, the analytical geometry curriculum in grade 12 focuses on circles, but we're going to start with the easy circles, those circles whose centers are on the origin. First of all, the equation for a circle whose center is on the origin. Here's a circle with its center on the origin, and there is its equation, x squared plus y squared equals r squared. The r in this case stands for the length of the radius of the circle. Now, what does this equation actually tell us? Well, it is an equation for generating the coordinates of every single point along the circumference of this circle. So, for instance, if this circle had a radius of length 6 units, then its equation would be x squared plus y squared equals 6 squared. 6 squared is 36, so we end up with this equation there. Oh, so where does this equation come from, you might ask? Well, here's a circle with its center at the origin and a point P on the circumference. If we wanted to work out the length of the radius, in other words, the length of OP, we would have to use the distance formula, which looks like this. But now when I substitute in the coordinates of P and the coordinates of the origin into my distance formula, I get this, because the coordinates of P are x and y, there they are, and the coordinates of the origin are 0 and 0. So when I simplify this, I end up with x squared plus y squared equals r squared. That, ladies and gentlemen, is where the formula comes from. Something you should know, when the formula for a circle whose center is on the origin is written in standard form, all three of these terms will be positive. That's positive and that's positive. If you come across an equation that is written in standard form where one of these terms is, one or more I should say, is negative, then it is not a circle. It is an imposter. Here's an example. Determine the equation of a circle with a center on the origin that goes through the point A, whose coordinates are 5 and -2. Well, as with much analytical geometry, we start with the formula. There it is. And all we do is substitute in the coordinates of point A in place of the x and the y in the formula. There we go. Work all of that out using your brain and get to this point. Now, you might be tempted to square root 29 to find out what r is, but we don't need to do that because in the equation we are required to use r squared. So it is already in the form that we require, so we can just plug it into the equation like that. There we go. That is the answer. Oh, look, it's Superman. Moving steadily along. A third example. A circle with a center on the origin goes through point B. If the diameter of the circle is 18 units, determine the value of x. Well, our equation calls for radius squared. So first, we've got to work out what the radius is. If the diameter is 18, that means the radius is 9. That means the equation of the circle is going to be this. X squared plus y squared equals 9 squared. Of course, 9 squared is 81. Now that we have this, we can substitute in what we know from our equation. We know what the y coordinate is 7. So we substitute in 7 in place of the y in our formula, work all of that out, and we get an x coordinate of 4√2. There we go. Done. Example number 4. The straight line y plus x equals 1 cuts through the circle x squared plus y squared equals 25 at the points A and B. Determine the coordinates of A and B. So let's do A first. How to determine the coordinates of A and B? Well, first we need to get the equation here for a straight line into its standard form. There it is. Then, if I'm trying to find the coordinates where two lines intersect, I'm going to have to make them equal to each other using simultaneous equations. Oh, wait. First, there's a little diagram to help us. There's the circle, there's the line, there's A and B. Oh. So let's use simultaneous equations. This can be equation 1, that's the equation of our straight line. The equation of our circle will be equation number 2. And now we just do simultaneous equations. Substitute 1 into 2. There we go. Work all of that out. Wonderful. Just the press of a button and it all just appears on my screen. Now you'll notice I get 2 x coordinates, and that is right. Come back, cursor. That is right because we've got 2 points of intersection. So we would expect to get two x-coordinates. This is clearly the x-coordinate for B, and that is clearly the x-coordinate for A. Now I substitute those x-coordinates back into equation number 1, like that. And so there's the coordinates of B, and like that. And there's the coordinates of A. All pretty straightforward. Right, now, next question B. Determine the midpoint M of line AB. Well, to work out the midpoint, we use the midpoint formula. Do you remember that from grade 10? There it is. Now we plug in all our information for coordinates A and B. There we go. And that is our midpoint. Question C. Sorry, the red box of doom. There it is. Question C said, prove that OM is perpendicular to AB. Well, first we're going to work out the gradient of OM. We know what the coordinates of M are, so we can work out the gradient of OM using the gradient formula. There it is. The gradient of OM is 1. Next, we need to work out the gradient of AB, and we already know what the gradient is because we have its equation in the question. So in the question, the gradient of AB was -1. Whoopsie. That should have been a negative there. Naughty me. So this should read the gradient of AB, which we know from its equation is -1. 1 times -1 equals -1. You'll recall from grade 10 analytical geometry that if two lines are perpendicular, then the product of their gradients will be -1. So this gradient was 1. The gradient of AB was -1. When we times them together, we get a product of -1, which means the two lines are perpendicular. Huzzah! Okay, bye-bye.